Geez, what does that say about you and all the airplanes you flew are in a museum somewhere? You've heard this before. People will come up and say, I'm glad to be here. But I'm glad to be here. This museum that you're in tonight is a much improved version of the museum that I was privileged to go to many, many times 60 years ago. Pestered my mom and dad to take me to the museum, and they would frequently bring me down to what was then the Air Force Museum. And so if you'll bear with me for 30 seconds, I'd like to show you what the world was like 60 years ago at the Air Force Museum. Now, this was 8mm movie film. It's 60 years old, so the colors are pretty washed out. But I think you can get an idea of what it looked like back then. That's what it looked like 60 years ago. So it's good to be back here. It's always good. I try to stop in the museum as often as possible because I visit my old friends that I've known for 60 years. And I hope you enjoy it as much as I have over the years. Tonight, I want to talk about the F-22, the Raptor. And what I would like to do is go backwards in time. And I'd like to show you the genesis of this airplane from the very rudimentary ideas that spawned it to where it is today. And the reason I do that is because we as civilians many times hear the argument that this is a artifact of the Cold War. And there is no Cold War. There is no Soviet Union. So why did we spend the billions of dollars on this airplane, and is it even relevant today? So what I'll do is I'll show you how we came to the decision, and then I'll end it up with why I think it is relevant, and I think you'll be able to see how it is relevant to what's going on in the world right now today. It was 18 years ago when we made the first flight on the first F-22 out of Marietta, Georgia. It was 25 years ago when we prototyped the concepts that would lead to the F-22 Raptor. And there were two competing designs. One was by a team of Northrop and McDonnell Douglas with the YF-23, which you see at the top, and another with the Lockheed, Boeing, and General Dynamics team, which had the YF-22, which you see on the bottom. And we'll talk a little bit more about that. But almost a half a century ago, but to be more exact, 44 years ago, the first rudimentary ideas of this kind of aircraft were being bantered about. And to put that in perspective, in 1971, the F-15 still hadn't flown. The F-16 was still 2 years away from flight. And the F-18 was even further away, 7 more years before it would fly. And we were fighting the Vietnam War. Now, had Congress known that there were people in the Air Force looking at a new fighter, they'd have probably blown a gasket. Because they would have said, for crying out loud, we've just given you in the Navy 3 brand new fighters. You haven't even flown them yet, and you want another toy? What is wrong with you people? So the question is, why would the Air Force have undertaken that? And to answer that question, you need to look back on history. And I've taken a 100-year span from 1915 to 2015 to look at. And you see the relevant major events, World War I, World War II, Korea, and so forth, Vietnam, on the bottom there. And if you look at 1915, you see that the airplane was used as a weapon. And the common weapon was to mount a machine gun firing forward on the early biplanes and monoplanes, and shooting down other aircraft or shooting ground targets. And for every weapon of war, there is a counter for the weapon of war. And the counter for the aircraft with a machine gun was a machine gun on a trolley or dolly that could be traversed and shot at the aircraft. Now, these are called ballistic weapons. In other words, when the bullet leaves the barrel, it is under the control of God's gravity and aerodynamics, and the bullet has a trajectory that's predetermined. So if the target moves after the bullet is fired, the bullet misses. It's called a ballistic weapon. But things began to change after World War II in the 1950s when we introduced a new class of weapons into aircraft, and that was the missile. But it wasn't just a missile. It was a missile guided by a radar. And now you could maneuver the bullet as it flew out. And for every weapon, there's a counter weapon. And the counter weapon was a missile from the ground, a surface-to-air missile or a SAM missile, also guided by radar, that could track and shoot down the airplane. And you see that the ballistic weapons at the top from World War I continue to this day. They are still put on airplanes and they're still used as ground weapons against aircraft. But we've added to it the guided missile. Now, in Vietnam, we faced the SA-2 missile. This was a Mach 3 missile that was designed to shoot down bomber aircraft. The Soviet doctrine was to shoot 2 missiles at every target that you had. In a moment, you'll see the first missile go off. It has a booster on it. The booster drops away, and the missile disappears. Until it starts conning, you don't see anything. But I want you to watch this contrail. You also hear the second missile coming up. This is a target in the upper left-hand side. You see the target up here. It's under a parachute, so it's a test run. But look at this missile, zigging and zagging very rapidly. It's doing about Mach 3. It's probably about 6 miles away from us at this time. It's looking for the target that's mounted right at the bottom below the 2 parachutes. Boom. It hits the first one. There's still a chunk coming out of the piece that he hit, and the second missile sees that chunk and goes after it. Bam. So what you see here is a bullet with a brain. That missile, it can rapidly change position, and the aircraft has to do something very drastic to avoid getting hit. This is what happened in Vietnam. It became a major influence on weaponry and our air power in Vietnam. I like to call this the picture 5 seconds after. If you were to back this picture up 5 seconds, you'd see that the F-105, which is on fire here on the right side, you'd see him coincident with this large puff of smoke and this contrail. That puff of smoke is from a SA-2 missile that has exploded. It has thousands of steel pellets in it. They come out like a shotgun shell, and they're very devastating. 5 seconds later, we see the airplane on fire and going down. One of the ways that we avoided these things was to see them and try to outmaneuver them. But at nighttime, you had no way of knowing where they were at or how to outmaneuver them. And a lot of the battles that we had, particularly late in the war, were at nighttime. And you'll get a sense from this short clip of the unpredictability and the difficulty of operating at night. This is from the ground. This is from the North Vietnamese point of view. 15 B-52s were lost during Christmas of 1972. It was devastating to the bomber crews. And there you see one of the B-52s going down. To actually see that, it looked like a firefall out of the sky. Very, very sobering experience. So the marriage between a weapon and a radar was what we were faced with, and we had to figure out how do you counter something like this. And the solution in 1972 were these three things. We took chaff and flare, which are simply pieces of metallic strips, very thin metallic strips, used first in World War II. We dropped them, and that helped blind the radar. Electronic jammers, in a similar way, electronically put fuzz or noise on the scope of the radar operator so he couldn't see his target. And finally, we would simply get very low. If you get down in the weeds, then they can't see you with the radar. And all these things worked up to a point. For example, when you're low altitude, what's called terrain masking, you're out of line of sight of the radar, but you also can't see your target either. So at some point, you've eventually got to pull the airplane up to visually acquire your target. And when you pull your airplane up, the radar sees you. So these were only partial solutions to the problem. But things were about to get a lot worse. The Soviet doctrine was to control their aircraft by ground controllers. So they had a man on the ground at a radar scope, and they would tell him, the pilot, okay, afterburner now, turn right, climb, descend, fire your missile. It was all by radio control from the ground, which meant that the ground controller had to be in a relatively close range to the aircraft he was controlling. But by 1975, the Soviets had introduced their AWACS airplanes, Airborne Warning and Control. The same controllers could now fly inside this airplane, and it could be placed anywhere, and they could direct their fighters. But in addition, you see this large radome on top of the back of the airplane. That now had the new radars that could look down and see airplanes down against the ground. So now you couldn't hide yourself in the ground clutter because they will see you from above. At the same time, they introduced a new series of fighters that were equal to or better than our best fighters. But more importantly, they also had radars that could look down on you, and they had missiles that could shoot down on you. So they took away our ability to hide ourselves in the terrain. And finally, they upped the game with their surface-to-air missiles. They became faster, they became more maneuverable, they became less susceptible to jamming. And so all of these things together made it extremely difficult, if not impossible, for our current fighters to get into certain areas. We could not penetrate areas that were defended with these weapons. And it's called area denial. So we had to have some way of countering these radar-guided bullets with a brain in them. And it required something radically different. So there were two links required with the radar. One is you had to have radar with the missile, and you have to have radar with a target. And those two solutions allowed the missile to be guided and hit the target. So somebody came up with the idea, well, okay, instead of worrying about trying to jam the radar, what if the target was just invisible to start with? And the radar couldn't do anything. So what did we know about invisible airplanes? Well, we actually knew quite a bit, thanks to Wonder Woman, who perspicaciously pointed out to us that it's probably radar-proof, and number two, somebody probably pay a pretty penny for this. And she was absolutely right. But we actually had some experience with aircraft that had low radar signature. The term stealth was used initially, meaning it was difficult to see these airplanes. The first one was in World War II. It was a German-designed fighter. We call it Generation Zero Stealth. This was a high subsonic airplane, quite maneuverable. Had gas-guzzling jet engines, so its range was pretty short. But it was quite stealthy, very difficult to detect with radars of the World War II vintage. Advanced the problem a few years, and by the late 1950s, the SR-71 Blackbird was flying. And now it was an extremely fast airplane, Mach 3 plus, but pretty much straight and level. It was not a fighter. It was limited payload, cameras in this case, carried internally, but it could go long distances at supersonic speeds. There were over 4,000 surface-to-air missiles fired at these airplanes in the course of their operational life. Not one missile hit the SR-71. Speed alone could help defeat these missiles. By the time the enemy saw you, reacted, got the missile in the air, and the missile tried to chase you down, you were gone at Mach 3 plus speeds. It was also rudimentary stealth in shaping. We call this Generation 1 stealth. Generation 2 stealth scares the aerodynamicists to pieces. This is a series of flat plates flying in formation. It has absolutely no aerodynamic benefit whatsoever. But it is extremely small from a radar target point of view. It is a high subsonic airplane again. It's not a fighter. It can maneuver, but it is not fighter-like maneuverability. It carries all of its weapons internally, so it's somewhat limited in its payload. It does have air refueling, but without air refueling, it's somewhat limited in its range. It's Generation 2 stealth. Generation 3 starts to look more like an airplane in terms of it's no longer the flat plates flying in formation. The B-2 bomber is, again, high subsonic, pretty much straight and level, can carry a tremendous number of bombs internally, and it has very long range. So if you've been keeping a score and you said, okay, I want to build a fighter, and the things this fighter's got to have, it's got to be stealthy, difficult to see, it's got to be able to go long ranges supersonic, and it's got to be highly maneuverable because it's a fighter. And if you look at those generations that we just looked at, you see that none of them could fulfill all the requirements. They're weak in either supersonic range or maneuverability, but none of them were true fighters. So what we were going to attempt to do was build a true fighter that had all three of those characteristics, and that was the challenge. For 10 years, the Air Force studied this problem, 1971 to 81, and you see this alphabet soup of acronyms down here. They tapped into the laboratories, the national laboratories. They tapped into think tanks in the Department of Defense and in the Air Force to try to determine, well, what is this advanced tactical fighter that we're looking for? How do you describe it? And there was, at that time, no consensus. Was this an air-to-ground machine, or was it an air-to-air machine? And there was no consensus even on stealth, because at this time, stealth wasn't thought to be practical for a fighter-like aircraft. By 1981, they began to ask the contractors, well, what do you people think we can do in terms of stealthy airplanes or non-stealthy airplanes? And the contractors came back with two different solutions. On the left side are air-to-ground solutions, air-to-air solutions. And on the right side are air-to-ground solutions. And they put it out to 9 companies. Only 7 companies responded. This is what they had. They ranged from the upper left-hand side of the Northrop small diminutive fighters to the lower right side, which is the Gigantosaurus Lockheed design that kind of is reminiscent of the SR-71. And some of them, like the Boeing airplane, had to go to swing wings for air-to-ground and not swing wings for air-to-air. So there was still a question mark of how you approached the problem and what was the form that this airplane would take. Interesting enough, even by 1981, stealth was not considered a possibility. After all these studies, there were certain things that were found to be essential to an advanced tactical fighter. The first was invisible, and I've already said that that word is easy to remember, invisible, but it's not. It's hard to detect, hard to see. That's what it really means. Let me give you an example here. Liu Belin is a Chinese performance artist, and he's sometimes known as the master of disguise or the invisible man. Now, Liu Belin is hard to see, even though he's standing right in front of you. Everybody got that? Okay. Let me see where my... I don't think we've got a laser pointer up here right now. If one of the guys can bring me up that laser pointer, I'd like to use that. But I'll tell you what. If you look right up here, you can see a part of his head and his eyes. His right shoulder is over here, and his left shoulder is over here. And the dead giveaway is his pants right here, okay? I think you would agree that Liu Belin is difficult to see, difficult to detect. But stealth is more than one medium. The medium we're looking at is visual. We can't see him. But if we were to take an infrared camera and photograph this scene, Liu Belin would stand out with his 98.6 degree body like a sore thumb against the 34 degree vegetables behind him. So to be truly stealthy, you have to consider all the sensors that can detect you. Radar is one of them, certainly, but so is infrared. The second item is omniscient, all-knowing. It's not enough to be invisible. You have to be able to reach out and find the enemy. Example. The traffic cop parks his vehicle under a bridge abutment off the side of the road somewhere over the end of a hump, and he becomes stealthy. He has a low visual signature. And then he takes out his sensor to catch you speeding. And as soon as he takes his sensor and points it towards you, he gives himself away because you, being smart, have bought a fuzzbuster and you will counter him and slow down before he can measure your speed. So he is not omniscient in the sense that we have to have in these airplanes. We have to be able to reach out and touch the enemy, and they never know you're there. We talked about the supersonic for long distances, and we talked about super maneuverability. The super maneuverability is the ability to outmaneuver the enemy if you're caught in the classical dogfight. So those were the four characteristics that we had to design. And then they said, engineers, by the way, while you're doing that, make sure it's reliable, maintainable, supportable, and affordable. Shouldn't be too hard to do and not cost $1 trillion. So that was the challenge. By 1986, it had become clear that, yes, stealth could be used in a fighter-like aircraft, but we needed to demonstrate and validate that the technologies we were looking at could be achieved. And it wasn't what could be achieved in 1986. It's what we thought could be achieved in the year 2005. So we were going to somehow look out in the future and predict what technologies would be available to us in the future. The contractors were allowed to define what the ATF was. There were no massive specifications for it because the Air Force wasn't sure exactly what it was. So they were given free rein to explore concepts. They were also given free rein to test the airplane as they saw fit. The airplanes were not tested to the same levels or to the same things. Each contractor did their own thing to find out what was risky in their design and how to minimize those risks. So it's hard today to make an apples-to-apples comparison by looking at data. It doesn't exist. And the contractors were asked to cough up 1/2 of the cost of the program. There was only one sure thing when this competition started, and that is that one team was going to lose a lot of money. I've always said that the Air Force SPO was responsible for a brilliantly managed program. They were trying to force the technology into the future, and they had to control it in such a way that these demonstrators were viable and useful when they got done with them. Rick Abel is down here up front. He was the chief engineer for the Air Force here at Wright-Patt. Brigadier General Jim Thane was the SPO director at the time, and they handled this program brilliantly in the sense that they kept an even hand on both contractors. No contractor got the upper hand. They were all offered the same opportunities. Thank you. They were all offered the same opportunities. As a result, at the end of the competition, the Air Force operational units were given 2 choices, both capable of doing the job of an advanced tactical fighter. And this was a direct result of the guidance and the careful management of the SPO on this program. Is that how you tell me to say that, Rick? No. Okay, so the question was, is the ATF probable in the year 2005? It lasted for 2 years. The winner was the YF-22, and it was ordered into production. But the airplanes, which we see today and which you can see out here on the floor, were only 1/3 of the program. There was another third of the program just to develop the avionics, and the Boeing team had a Boeing 757. You notice that on the back of the fuselage is the wing of an ATF, and on the nose is the radome of an ATF, and stuffed inside were many computers that were used to emulate computers of the year 2005 in terms of capacity, power, and speed. And this is how we tested those omniscient avionics, the ones that can see you, but you can't see us. Little known facts. Originally, there were no prototypes. The contract was let with no prototypes, and about 5 months before contract award, they decided to put prototypes in there. The only requirement is the airplane flies one time. No other requirements. It was not a fly-off, as I mentioned. The testing was dissimilar, and so there was not a fight. No pilot ever flew both the YF-22 and the YF-23 to keep them separated. I mentioned that the airplanes were only 1/3 of the program. A large portion of $1.1 billion was spent in these other areas. And they were beyond the state of the art in 1986. None of the things that we simulated or emulated in terms of avionics could be done in 1986 in the size and capacities that would fit into a fighter. And Lockheed, as I mentioned, they had to cough up $1.1 billion along with their suppliers to play the game. So, this was the prototype, and what Lockheed was to do was to convert this into an actual operational flying fighting airplane. The program, which was called Engineering and Manufacturing Development, lasted for 14 years. There were 9 test aircraft, 3 of which were just to test the flying qualities of the airplane and the airframe itself. The other 6 were to test the omniscient avionics. About 3,500 flights and 7,600 flight hours. So the one figure I want to call to your attention is this one, 2,600, because I'm going to show you what 2,600 encompasses. By comparison, there were only 3,500 avionics test missions. So a large portion of the testing went into this, what was called envelope expansion. We'll talk about that. So this is how the program started. The biggest problem the Air Force has and the contractor has and that you have is it's impossible, because of classifications of these kind of airplanes, to really tell you what's special about them. As you look at the picture of the F-22 tonight, you can tell yourself, yeah, that kind of sort of looks like an F-15 or an F-18. It's got 2 vertical tails and 2 horizontal tails and 2 wings and engine intakes. So to the casual observer, you don't see anything different. And you're tempted to air show and watch airplanes like Soviet airplanes and the F-22 do some fancy maneuvers and say, well, that airplane can do something that that airplane can't, therefore that airplane is the better airplane. And that's missing the point entirely, because what the F-22 can do is classified and difficult to explain. So my task tonight is to see if I can explain to you classified things without being thrown in jail. I hope you'll go along with me on this. See, we need a picture. We need a picture that you could walk out of this room and say, oh, he talked about invisible airplanes. That I understand now. We don't have that picture. So what we have to do is use some analogies. And this is the analogy I'll use. Now, this is very illustrative. Jodie Foster is in a darkened room. She knows that the enemy is nearby, but she cannot see or detect the enemy. On the other hand, Wild Bill is there with a pair of night vision goggles and can see exactly what's going on. His goggles don't emit any energy, so he is undetectable from a sensor point of view, unlike the highway patrolman with his radar gun. And he sees perfectly well in an environment where she cannot see. We actually saw this effect in the simulations. It is terrifying to go against an airplane like an F-22 and know he's right there and know he can shoot you and cannot find him. So that's the first part of it. But the second part of this little snippet is that stealthy airplanes have to consider all aspects of stealth. Does anybody know what the aspect of stealth is that got Wild Bill shot here? Audible. He cocked the gun, and Jodie Foster fired blindly and hit him. So if you don't cover yourself in terms of all the ways you can be sensed or detected, then you're not truly stealthy. So let me turn to the airplane itself and give you a quick overview of it. I've got a picture here of the prototype up here. Of course, this is the F-22. If you look closer, you'll see little differences in the wing shape and so forth. But what I want to really point out to you is why is a stealth airplane unique, and why it is that you can't take an existing airplane and simply declare it stealthy. Look at the angle on the leading edge of the wing. Notice it's repeated on the leading edge of the horizontal tail, and again on the trailing edge of the horizontal tail. And if you look closer, you'll see that same angle repeated on various little details on the airplane. And those angles are very important because they change the radar signature of the airplane and make it very difficult to detect. It's called an edge-aligned planform. And that's what is meant by that, and you'll see that on the B-2 if you look at it in a picture. The other thing about the airplane is its ability to vector the thrust. About plus or minus 20 degrees, here's the engine running on a test stand in afterburner. You can see it deflected down about 20 degrees. Why is this important? Remember, I'd used the term super maneuverability, the ability to outmaneuver another airplane. When you get extremely slow, there's not enough air that moves over the wings and the tails to really move the airplane around. So you become a rock, an uncontrolled rock falling down. But with this engine, it's putting out tremendous force all the time, including at zero airspeed. And now you can use that to actually move the nose around. And in fact, it actually allows the airplane to turn using the rudders. So the airplane can be maneuvered at extremely low airspeeds, hence the term super maneuverability. This class of airplane is also in its go-to-war configuration. So when you see it in the air show, it looks like this. That's the way it looks going into combat. There are no fuel tanks. There are no external stores. Everything is carried internally. So you see even the gun, the cannon from World War I, is carried inside with a little door that flips up, and the bullets shoot out over the top of the wing. Air-to-air Sidewinder missiles are carried in pouches or doors on the side of the engine intakes. And the larger AIM-120 missiles, the AMRAAM, and gravity bombs are carried, guided bombs, are carried in one or two weapons bays. Here is the left weapons bay open. There's a symmetrical weapons bay on the right side. So everything in terms of weaponry and fuel is carried internally in the airplanes. Reason? To keep your stealth signature down low. When you get ready for a first flight on a new airplane, it takes a lot of people. We had 30 engineers. We trained for 9 months for one flight. We simulated every conceivable emergency that we thought we could have and trained to where we reacted as a team instantaneously and talked with 30 people on an intercom, a common intercom net, without stepping all over each other, yelling and screaming. It was a supreme example of discipline. Let's see if I can run this. Doesn't want to run. So even though it's a single-seat airplane, it's never a one-person event. We rely as pilots on those people in the mission control room who have displays like the space shuttle has, and that they can come up with solutions to get the airplane and the pilot safely back on the ground. The first flight team was very special to me. We became a very close-knit group. We keep in touch to this day. It was one Air Force guy told me, he says, the whole flight, these guys looked disappointed. I said, disappointed? And he said, yeah, they just didn't have any emotions. They just looked disappointed to me. And I thought, that's exactly the way we wanted them to be. We had no problems during the first flight. And although they trained for 9 months on every possible emergency and were just ready and willing to go have something happen, nothing happened. And that's in large part due to the fact that you do train so hard. Okay, I showed you a slide and I said, remember 26,000 points. And that was the testing of the envelope expansion of the airplane. This is called a flight envelope. Every airplane has one. It's characterized by altitude on the left and speed on the bottom. And on the left side is where the airplane can fly level flight and no slower. The top is limited by something like human physiology at 50,000 feet, or maybe it's an engine limitation. On the right side here, it's usually limited by a Mach number like Mach 2, or some kind of engine heating or airframe heating. And down here, it's limited to what's called dynamic pressure. And all flight envelopes have this kind of characteristic to it. And what our job is to do is to check this thing out completely, everywhere, and make sure there are no gremlins or problems with the airplane or engine in the flight envelope. So we go to some nominal point in the middle where everything is safe. We begin to push out in speed at a given altitude, and we test slowly and gradually out till we can get the airplane to its maximum speed. And then we might go up in altitude and then down in altitude to the high Q situation until eventually you blanket this thing. And if you can imagine drawing 26,000 points inside that envelope, that was our task to test out this airplane. But it's not enough to test the envelope. You've always got to ask yourself, what happens if the pilot has a problem or makes a mistake? You don't want the airplane to fall apart just because it touches one of those boundaries. So we actually take the airplane and test beyond the operational boundary of the envelope. Over on the left side, you notice there's a lot more red over there. That's because airplanes can intentionally be flown to very low airspeeds. They may not be able to maintain level flight, but they can be flown to very low airspeeds. And that's one area where traditionally we have a lot of unknowns. Therefore, there'll be dragons out in those areas. But we do have to test that because pilots will fly out there and get themselves into those areas. To increase our productivity, we had to do air refueling and get qualified on the tankers. KC-135 on the left, KC-10 on the right. This is what it looks like from the boomer's position. The task is to fly to put that little tip inside the little receptacle right there on the back spine of the airplane. It's a good test of the airplane's flying qualities. It requires precision to inches to get it done. And I think you can see that in this video.
Raptor 02 also expands the air refueling envelope to the lowest speeds and highest altitudes planned for the F-22. At 220 knots calibrated airspeed and altitudes from 5,000 to 35,000 feet, the Raptor retains the excellent handling qualities seen from the very first air refueling tests. During these tests, the aircraft must be maneuvered to exact positions representing worst-case mispositioning behind the tanker, including very high positions with the air refueling boom pushed full forward. This demanding flying requires that the aircraft be positioned within inches of the desired location and held there as the tanker boom operator connects and disconnects from the F-22's refueling receptacle. The close positions are evident in these scenes from the chase aircraft, as well as from the cockpit of the F-22. The excellent handling qualities of the F-22 make this exercise particularly easy for the test pilots.
Now, you weren't supposed to say that last part. I'm not sure where it came from. The other things we do in terms of envelope expansions, we have to fire missiles. Now, we're not looking to guide the missiles. We're asking the question, will the missile leave the airplane without colliding with the airplane or doing damage to the airplane? What I've got here are two different examples. This is a relatively high-speed launch of an AIM-9, the air-to-air missile out of the side bays on the airplane right here. And this is a relatively slow-speed launch out of the airplane. Notice the flame here coming out into the weapons bay. So there's a possibility of damaging wiring and plumbing and other things as you shoot. So we test all of that. Here's a shot with the weapons bay with the AIM-120. It's a slow-speed shot. And you can see the missile leaving, igniting, and flying off. And this is one of the other things you check. What happens if you fly back through the smoke of the exhaust? A lot of engines don't like that and will compressor stall and flame out. Fortunately, the F-119 engine that we have in the airplane was bulletproof. But we had to test these anomalous conditions. This will give you an idea. It's kind of a quick and dirty of what it all looks like when you put it together.
In the weapons testing area, AIM-120 inert missiles are loaded into the F-22 main weapons bay for fit and functional checks. The aircraft has subsequently been flown with those missiles and will, in the near future, fly with the weapons bay doors open to gather data on noise and wind blast on the missiles and the equipment inside those bays.
AIM 120. Those are flares to decoy missiles that might be chasing you down. Gun firing. AIM 9. Dropping flares with the landing gear down. Firing the gun again. We have to test everything while the airplane's rolling, including shooting missiles while it's rolling. The airplane's capable of engaging multiple targets at a given time. You're going to see a sequence of 2 launches here coming up. There's a gun fire. There's the smoke being ingested. 1, 2 fire. So that'll give you some idea of some of the other envelope expansion work that we have to do. When we go to high angle attack, that area on the left side, it was all red where there be dragons. We don't know always what's going to happen. And when the airplane goes out of control in those regions, it sometimes can be unrecoverable and would go in. So what we do is we put this orange tripod thing on the back of the airplane. It has a parachute in it. It's ballistically deployed. So if you get into a condition that's out of control and the pilot can't recover, he pushes a button, the parachute comes out, stops the airplane, pitches it over, and when it's hanging vertically, cuts the parachute away and flies off, and we recover the airplane. This is a ground test that was done just to make sure that the system worked properly. We never had to use it. The airplane's tested at high angles of attack, upright and upside down. You see upside down here on the left. And you see what's called a tail slide on the right. You simply fly the airplane up till it's 0 airspeed and let it fall and see what it does. So let me give you an idea of what these look like. This first one is a tail slide. And like a lot of the things we do, we have to look at what happens if the pilot does something wrong. Will the airplane still survive? So one of the things the pilot can do wrong in this, he gets it up to 0 airspeed and suddenly the airplane's falling. He feels it falling backwards. He gets nervous and panicky. He starts moving the flight controls around and the engines around, trying to recover an airplane which has no airspeed on it. When he does that, the power to drive his hydraulic pumps is coming off the engines. And so as he pushes and pulls the stick around, he extracts power from the engine. And if he extracts enough power, the engines flame out. And if you flame out falling backwards on your rear end, you're in deep trouble. So we test the airplane and force it to see if it will flame out. So what you're going to hear is the test conductor say, stir mill. It means at the power setting you're at, stir that stick for all you're worth.
Stir mill.
And the airplane on its own just pitches down and it keeps on flying.
Incomplete.
Now, we also do things that pilots might say, oh, I'll never do that, but they will. This particular maneuver is a roll. Slow speed, the pilot starts a roll, and when he's here, he pushes full forward on the stick and holds it. And we want to see if the airplane remains in control. And it doesn't in this case. Here comes the roll. Here comes the push. You can see his tails when he comes up. They're full down. Once around.
Recovery all right.
Whoo.
Copy.
Hey, we're going to look at it from the pilot's point of view through the heads-up display. And I want you to listen to his words.
Ignition 3, 2, 1, now.
Roll. Push.
Forward. Yahoo. Yow. Whoa. Recovery all right. Recover. Controls release.
Controls released. He just takes his hands off of it. The airplane says, well, I know which way is forward.
Okay. Pull. Recovered. Recovered. Holy Copy that.
I think that was deleted, the expletive there. Sure. So, and those are the kind of things you look for. And what they do nowadays is they go back in with the software that's in the flight control system and they tune it up a little bit, and it won't do that anymore. The flight testing of the production airplane went on for 8 years. The first Raptor squadron became operational in 2005, so it's been in use for 10 years now. It was 34 years after it was conceived. It's only 187 of an original buy of 750 were built. And there's 6 Raptor squadrons that are operational today. But flight testing continues. They continually find newer computers, newer methods, and newer ways to use those capabilities in the Raptor. And so they're testing at Edwards with the airplane for future follow-on growth. So I want to conclude this by going back to where we started. Remember I said that after World War II, we saw this revolution in weaponry. The bullet with a brain, the radar-guided missile. And it evolved by 1975 until those systems were so potent that the existing airplanes we had could not even get into certain airspace without suffering unacceptable losses. And we called that area denial weapons. Okay? The counter technology to all this was stealth, sometimes called low observables, and you saw the evolution of those aircraft. But the thing that you want to note here is that Soviets and the Russians today have used this technology as export. And the reason they've used it for export is because it is a very good way of getting income. And so you'll find these weapon systems that I talked about spread around the world. A lot of people say the F-22 is a Cold War artifact, but I want to offer to you that it's a Cold War product. And the difference is this. Because the technology is around the world today, and because the technology is mobile, it can be redeployed anywhere in the world today, we could face an area denial situation anywhere in the world tomorrow. And Syria is a perfect example. Look how quickly the Russians moved their top-notch equipment into Syria. If they chose to deny us airspace, they have the capability of doing that against our current fighters. Airplanes like the F-22 can operate in that airspace and can survive and do the job. So that's what I would offer you. It's not a Cold War relic. It is a development from that period of time that still has a lot of relevancy today. So with that, I'll open it up to your questions and try to answer them.
Thanks, Paul.
Yep.
We have a basket that's going around. If you have questions, just raise your hand. Teresa can bring the basket, and then she'll bring the questions up here. I have a few to ask you, Paul, if you don't mind. You talked about the engines having thrust vectoring. Are there other characteristics of those engines which make them more advanced than engines, say, in the F-15 and F-16?
The engine's technology of today is quite good, and even on the F-15s and F-16s, the newest engines are quite good. They no longer suffer from compressor stalls or the engine failures that we saw in the past. They've learned to control them with digital controllers to such an extremely fine level that the engine operability, the ability to operate, we call it carefree abandon. You can take the throttle and slam it up and down anytime you want, any speed. The engine doesn't hiccup, doesn't do anything but respond and give you what thrust it can. So, no, it's not different in that regard. The thrust vectoring changes the dynamics of the airplane.
Okay, I'm going to switch spots with you here.
Yeah.
Then another question would be that the F-22 is a huge leap because of 4 characteristics.
Yeah.
So now that we have the leap to the F-22, what in your mind is that next great leap beyond the F-22? What characteristics?
I don't know. Honestly, I don't know because I'm not access to the latest things that are going on within the government. I hope that they are. It was 44 years ago when they started thinking about the ATF. I sure as heck hope They are thinking about the next generation. For every weapon, there is a counter weapon. So for the F-22, there will be a counter to the F-22. And people hopefully are looking ahead to what will be the next step to counter the counter to the F-22. But I don't know that.
We have a question from the audience. Any close call stories as either a combat pilot or a test pilot?
Well, what's that?
You don't have enough time to go through them all.
Yeah, there were some exciting times. No, the only thing, I had to bail out of an F-105 one time. In fact, a little side story, if you go out here in the Vietnam section, you'll see an F-105 out there. It's an F-105G, just like the one I flew. But it's not the one that's supposed to be there. The one that's supposed to be there is an F-105 that was flown by a guy by the name of Leo Thorsness. And Leo Thorsness is a Medal of Honor winner in the F-105. And his airplane was destined to be sitting out there on the floor. He told me a couple of months ago, he said, yeah, I used to call the museum every couple of months. I said, do you still have my airplane scheduled to be in the museum? Yes, sir, Mr. Thorsness. We're going to put it there. The airplane was crashed and destroyed in 1975. I crashed it. The engine quit, and there aren't too many alternatives when you only have a single engine. So we bailed out of that airplane, but I felt bad about that ever since.
I think this is kind of a rhetorical question, but it's worth asking. Can you buy life insurance easily?
No. Actually, that's a reasonable question. No, you cannot buy life insurance reasonably as a test pilot. So what Northrop did is they actually got a policy issued for each one of the test pilots on their life, and they paid the premiums on it because companies will not insure you.
Your opinion, is 187 enough given China and Russia?
Well, that's the essential question. It better be the right answer, but I'm concerned. Obviously, the Russians and particularly Chinese are developing their own versions of the stealth fighters, and they are capable of producing them in great numbers. So it's a valid question, and if 750 was the right answer to begin with, you kind of wonder if 187 is the right answer to end up with.
We have two questions that are related. How does the thrust vectoring engine compare to that of the Russian Su-27, and is thrust vectoring available throughout the speed envelope?
Okay. I don't know about the Russians. I've never flown the airplane. The Russians do have what's called some axisymmetric vectoring. The F-22 vectors up and down, plus or minus 20 degrees. The Russians have an eyeball kind of arrangement that lets them point the nozzle back, but all through 360 degrees of position. So you might say that that's better. The problem with low-speed fighting is, regardless of who you are and regardless of what capabilities you got, once you get slow, you're a target in space. So anybody that's not in your fight has a very easy shot against you, and particularly with the heat-seeking all-aspect missiles of today, getting slow and dogfighting is a very dangerous proposition. And the second part of the question was... all speeds. No, the thrust vectoring is used at low speeds. The airplane is quite capable of maneuvering once it gets above a certain speed. Just with the tails, the tails can take it to its maximum structural load limit. So you don't need any more, and it does it. The tails can take it there very quickly. So it's mainly a low-speed type of device.
We have a couple of questions asking for comments on the problem on the O2 system. Has it been identified, and if so, what was the fix?
I read the same books you do and the same newspapers. I have no inside knowledge since I retired of the details. They have found the fix. I believe it was your lungs have alveoli in them, small little sacs where the air is taken in and then broken down in the bloodstream. And my understanding was that the pressures that we breathe in the F-22 were sufficient to collapse some of the alveoli in your lungs and were causing these problems. I believe it's been solved, but it's part of the physiology side of airplanes. In the F-22, you had a mask, or oxygen mask, pressure mask, and they injected high-pressure air into your lungs, which would have exploded your lungs normally, except you wore a pressure jerkin that was simultaneously inflated to keep your lungs inside your body. And so you were being rammed, if you will, supercharged with air down your lungs. And so that's a little different environment than we've normally had in the past. And obviously it had some side effects.
Could you please highlight the differences of the production configuration from the museum's YF-22?
You don't have a YF-22. You have an F-22 number 3.
That's right, yeah, an EMD.
Yeah.
So I guess maybe the correct would be, what were the differences between the YF-22 and F-22A?
Yeah. If I could do it quickly, I'd whip back here to this one picture. I tell you what, the airplanes are similar, but quite different. Let me see if I can get a picture here. There we go. If you look at the wing sweep, look at this wing sweep here and the tip here. You can see it's not as swept here. You see there's an extra edge here going back here. We call these the cookie cutter tails. You can see how they're kind of cut out here. You don't see that here in the airplane. If you look at the leading edge of the intakes where the pilot's head is at, they're forward of the pilot's head. Here they're about in line with the pilot's head. So things were moved around. The main thing was, a lot of people don't know this, a prototype is a hodgepodge. You don't put the optimum equipment in a prototype because you'd have to uniquely design a hydraulic pump and a fuel pump and a this and a that uniquely for 2 airplanes. It'd be horribly expensive. So I know in the YF-23 we had parts off the space shuttle and helicopters and the T-37 and all kinds of airplanes went out and got various parts that worked. They worked fine. But they kept the cost down when you're only building 2. So these airplanes, the prototypes, they showed you aerodynamically what these airplanes were capable of, but they were not in any way production representative. So the main differences tend to be internal, with some external differences that you can see. Well, and it's a good point. These prototypes were not designed to be tested for low observables. We did that with a full-scale model of the airplane against radars to make sure that the stealth characteristics were what we predicted. But the prototypes were not made to be tested against radars.
I think naturally there are several questions asking about comparing the YF-23 with the YF-22. Of course, you flew the F-22 EMD, which was different, but would you have any comments about differences between the F-23 and F-22?
No.
That's an easy answer.
No pilot ever flew both of them.
Okay. What are your thoughts on the F-35 program and how it was run differently than the F-22 acquisition?
The F-35 is a different kind of airplane. It's basically an air-to-ground airplane. It has air-to-air capability, but it's mainly an air-to-ground airplane. It has far more sensors, these magic sensors, than the F-22 does, all optimized for ground targeting. So it has a different role in life. It's a complex airplane. It's complex from an avionics, from a software coding point of view. I can't remember how many millions of lines of code, but a lot. And it has its growing problems, but it is getting there. And it is not the first airplane that's had problems in its development cycle, and it won't be the last airplane. So I believe in time it will prove itself to be quite a potent weapon.
Could you comment on the crash on the runway at Edwards during testing?
Okay, I think what you're referring to is the YF-22. This was the second airplane, the second prototype. And that was caused by a thrust vectoring problem. It had thrust vectoring, just like we've looked at. But they were supposed, by procedure, to turn off the thrust vectoring when they were close to the ground and landing. And they had gotten to a habit pattern of leaving the thrust vectoring on, which turned out to be a cliff edge that was waiting there for the right pilot to step over the edge. In fact, several of the pilots had come close to the edge as they looked at the data after the accident and didn't step over it. But Tom Morgenfeld, the Lockheed pilot that day, happened to be raising his landing gear, which instantly changed the gains on the tails and the thrust vectoring and caused an abrupt pitch down, which he saw, and corrected with an abrupt pull back on the stick, which caused an abrupt pitch up, and which caused him to think his airplane was going to go straight up and stall. So he pushed over, and you saw the results, a series of what we call pilot-induced oscillations to impact. And so that's a quick and dirty of what happened.
And I think we have a last question here. It's kind of a two-parter. What was your most dangerous moment as a test pilot, and what time were you the most scared?
I don't think I had really any dangerous moments. So I had failures, I had things go wrong, but you're trained to handle them. You're trained to look at life very dispassionately. And so I don't recall any times when I was scared, terrified, or otherwise, but I had some things that got my attention. People asked me that question once before, and they said, what was the scariest thing about combat? And I thought about that a long time, and there were some scary times there when people were trying to kill you. That's not nice. But I thought about it, and I said, the scariest thing about combat is the night after your first day of combat. And the reason that's the scariest is because on the first day of combat, you will pump adrenaline into your body at levels that you have never experienced before. It is terrifying, and your body reacts to it. But you have to come back that night, you have to lay your head on the pillow, and you have to go to sleep, because the next day it's going to start all over again, and somebody's going to try to kill you again. And what you come to grips with at that moment in your life is a promise you made. You promised to preserve, protect, and defend the Constitution of the United States against all enemies, foreign and domestic. And what they didn't say, but which is implied in there, you will protect the Constitution of the United States up to and including your death. And it's only at that time do you realize what promise you'd made. And now you must come to grips with, will I keep my promise, or will I be so scared that I'll tell them I can't fly anymore? And so for me, looking back in retrospective, that was the scariest part of combat, the night after your first day of combat.